Good evening friends, my name is Sandeep. Today I am going to explain my subject is drives and my topic is about optimum current of control for high speed axial gap permanent magnet synchronous motor. Abstract the high speed 2000 rpm axial gap permanent magnet synchronous motor has been conduct, conducted toward and new developed algorithm due to the high speed of implementation using developed vector strategy PMW and the difficult and the new efficient and the optimized algorithm torque and problem for salient type MP. The output voltage and torque angle different speed with further form of optimum DQ access current so that decoupled control can be applied to 6 inverter. The complete drive system could be implemented using open loop voltage and torque angle and the track closed control with one control and by closed both open and closed loop control system has been and the closed control system is fabricated for 3-phase 8 poles 460 volts 27 HP axial gap PM motor. Although torque postulating cannot be avoided with 6-step inverter, actuation is quite smooth due to high load inertia. Introduction. Axial gap synchronous machines have several advantages: high efficiency, high power density, and a wide range of for speed implementation. And using decoupled vector control strategy along with the PMW inverter could be difficult and inefficient. Conventional 6-step inverter is the favorite when efficiency and high speed application considered. For the high power applications, it is necessary to reduce the current stress of switching. A torque EMP maximization using DQ current decoupled vector has been proposed in the interior PM machine. However, optimization has yet been applied to voltage per is a control scheme. In DQ control decoupled vector flux is controlled by D axis current and torque is controlled by Q axis. In voltage per head frequency control flux and can be controlled by voltage can be controlled by torque, and with the voltage torque angle has to control completes in the control in paper constant torque acceleration control system using actual PM motor design using microcomputer control the criteria acceleration inertia while overcoming 2000 rpm 5 minutes or less by developing constant motor implementation of torque by amps control design voltage by frequency control the voltage and torque torque angle transactions are solved by the stock in the tables for microprocessor optimization and torque and derived functions and DQ constraints. Solving DQ currents for optimization torque new algorithms using Newton-Raphson iteration method is developed. The complete drive systems could be implemented using open loop optimum voltage and torque and transactions closed loop control with one variable taken look up the table. The other variable controlled by closed loop PA control with the open loop and closed loop having stimulated using PCE Simon and closed control system fabricated 3-phase 8 poles 460 volts 27 SP axial PM motor. Although the torque postulating can be avoided in 6 steps inverter isolation smooth due to high load inertia machine structure modeling. The axial gap PM motor consists of thin armature stator winding and thin rotor disc. Because the low inertia in the disc type machine suited for reliable high frequency and high speed operation, the stator of design ruggedness and heat transfer silency of the axial PM motor and dependency of with the number of small air gap few poles will have higher salience and vice versa. Figure 1. The stator assembly showing the teeth and winding pair or to encapsulating. Figure 2. The rotation containing 8 neodymium iron boron alloy magnet. Figure 3 shows that the machine model of the silence of synchronously rotating reference frame. The dynamic equation and the represented by the mathematical model can be derived from the above. DQ element circuits shows the state equations including speed and torque dynamics. Diq by dt 1 by LQA VQS minus RS IQ minus WE LDI DS E1 and dW dWr by dt TE minus TL by J TE3 and LD LQS IDS plus IJ by W into IQS, where the R is starter resistance, LQA is Q axis inductance, LS is Q axis inductance, and EF is counter EMF, W is operating frequency, VQS is equal to Q axial component, VDS D axis voltage component, IQS Q axis current component, IDS D axis current component, WR rotor angular frequency, T is generated torque, TL load torque, J inertia and P pole in steady state di by dt, and the equivalent circuit can be simplified without dynamic quantity. The voltage balance equations can be represented by VDS IDS RS minus IQS WE LS WE is equal to EF plus IQS RS plus IDS WE EE. Figure 3 equations synchronous rotating reference frame. Optimum torque by AMP control for surface mounted PM machines and efficiency optimization has been proposed to minimize the loss of voltage trajectory functions of frequency. This control does not torque angle has control variable is therefore typical scalar control in vector control optimization torques amps and the method for interior permanent magnet IMP machines has been proposed. The traction control, in fact, the scheme minimizes the starter current for specification torque and major advance of inverter switch device and increasing efficiency the function and the minimizing the starter current in the form where torque is functions of DQ axis current by varying IQS for given torque minimum current trajectory can be searched for and found where whole family of DQ current poles. The search is required for each torque and tangents were finding a set of torque values. This paper proposed numerically optimization approach to solve the minimum current trajectory problems, which indeed saves a lot computing time. The optimization is formatted 3.1 of optimizing algorithm. The minimum current problem is posed as many I square S IDS IQS such that TE IDS and IQ is equal to TE I2S is equal to IDS plus IQA and TE is a given torque value. Thank you.